Welcome to tonight's Northern Grapes Project webinar. My name is Alex Caberly, and I'm a program assistant for the Northern Grapes Project. Thank you for tuning in today. Today's webinar is Put a Cork in It, an update on wine closures with Katharine Mansfield. Katharine Mansfield is an associate professor of Enology at Cornell University. As leader of the Enology team for the Northern Grapes Project, Katharine is focused on aiding small regional wineries through Enology extension, wine sensory evaluation, and defining regional identity in developing wine growing areas. Some of her current research projects at Cornell include fermentation nutrition, the sensory impact of wine phenolics, acid adjustments in cool and cold climate wine types, and defining the concepts of regional and cultivar typicity. Remember that as a participant in the webinar, we ask that you keep microphones muted if you have them. If you are having any technical difficulties, please type a note in the chat pod over to the right side of your screen, and I'll do what I can to help. If you have questions, please type them in the chat pod as well. We'll have a question and answer session after each presentation, and feel free to type in your questions anytime if you have them. The 5-year Northern Grapes Project concluded in August 2016, but we have been able to continue with the Northern Grapes webinar series this year through May 2017, thanks to these generous industry donations. Now I'd like to turn it over to Katharine Mansfield for tonight's presentation.
Thanks, Alex. Can everybody hear me now? Oh, yeah, I am now the presenter. Excellent. Okay.
Yeah, and
good.
You are presenting.
Fabulous. Okay, I have all the controls. Haha. Anyway, thanks to everybody who's tuning in tonight. It is certainly a beautiful evening here where Alex and I are. So I appreciate if it's the same where you are, I appreciate your coming inside to look at a screen instead of enjoying the weather. But what we are going to talk about today is basically a review of wine closures. We haven't looked at this for a while in the context of our webinars, if perhaps ever. And it's important now, not so much because there are a million new closures on the market, so much as that there's been a lot of good research recently that has given us a better understanding of what the closures that are available do to our wine over time. So what I'm going to do today is, for the first half of this talk, just sort of review some of the options that are out there and where they come from, and then afterwards, I've got lots of good information about sort of what that means in terms of the choices that you can make regarding your wines. So with that, we will go ahead and start. Of course, most of us, I assume you are listening to this talk because you use bottles for your wines. And from a packaging point of view, in many ways, bottles are phenomenal. Yes, they are heavy and breakable and relatively expensive compared to, say, plastic bags, but they are inert in terms of the wine and don't interact with it to any great extent. So the problem, actually to any extent, so the problem that we have then when we're figuring out how to package our wine to keep it in the same shape that we leave it when our consumers taste it is putting a closure in there. It is pretty much impossible for us to bottle our wines and then seal up the neck of the bottle, with just molten glass and keep it therefore airtight. That is not an option that is very useful, although it's kind of funny to think about. So we, for years, have used corks and other closures in order to seal up that last bit of our wine. Because, really what it comes down to is this. Bottling is the last chance that we have to check our wine for all of the sensory and chemical characteristics before we send it out into the world to fend for itself. The bottle and whatever closure we use then are the only defense we have against spoilage and also against changes in aroma and flavor. So the steps that we use in our bottling process and during bottling are pretty important. We want to make sure that the wine and the packaging and all the methods that we use to get the wine in the packaging are optimal. So while talking about optimal bottling practices are a completely different, probably multiple hour-long discussion in itself, I do want to touch on at least a couple of things. The first, of course, is that Our major defenses against microorganisms in our wine is SO2. Pictured here, you can see a sort of a cartoon of a sulfur dioxide or SO2 free molecular molecule. Free molecular SO2, as you probably know, is the active form of SO2 that we monitor throughout the winemaking process, and it's absolutely essential that we take care of that, check it right before bottling. In many ways, the bottling process is the most dangerous of all the things we do to our grapes during the processing, although they aren't grapes at that point. But from grapes to getting the wine out to the consumer, bottling is the place where we take the most risks. It's coming in contact with many different surfaces, all of which can be contaminated and can contaminate the wine, and of course with air. So just as a reminder, just prior to bottling, we want free molecular SO2 levels to be 0.7 to 0.8 milligrams per liter or parts per million. Those are the same. Milligrams per liter equals parts per million, so we use this interchangeably. For white wines, although depending on the aromatic characteristics of the wine, 0.8 parts per million might be too high. That might be perceptible, especially if you're dealing with a wine that isn't strongly aromatic like a Le Crescent or a Gewürztraminer or something like this. So you may need to go a little bit lighter if you have a relatively neutral white wine. Also, and we'll talk about this in more detail later, of course, the type of closure that you're using and the time that you intend to bottle age your wine before release are things you should take into consideration. If you know, for instance, that your wine will be released and consumed in the few months just following bottling, if it's a light fruity wine that you want to get out to your consumers so that they can open and drink right away, you might want to aim for a slightly lower SO2. For instance, we have found just following say the past 15 years, as people switch to more and more synthetic corks or synthetic closures, which research has shown let in more oxygen over time, we found that winemakers were therefore appropriately upping their additions of sulfur dioxide just before bottling, but if the wine was then sold, released, and opened relatively quickly, that SO2 hadn't been interacting with as much oxygen as you would get over the course of several months, and so the SO2 levels were too high. So keep in mind that, an addition that you make for a wine that needs to age for a year is going to be less than what you would want to make for something that would happen relatively quickly. Red wines are a little bit different because of all the phenolic compounds in there, the tannins and other things. We have more protection in a red wine from spoilage and from oxidation. So the goal for red wine, free sulfur dioxide, is 0.5 parts per million or milligrams per liter. And in both cases, we want total SO2 to be around 110 milligrams per liter or less. So if that 110 number looks really large compared to the 0.5 and the 0.8, remember that free molecular SO2 is a calculation that we make. We determine our free SO2, which is probably something more like 50 or 30 parts per million, and then use a pH-related equation to calculate what the free molecular is that we have. So that is just a fraction of all the SO2 that is in our wine. The total SO2, of course, is the sum of the free SO2 versus the bound SO2. So that number is going to be a whole lot higher than just the free molecular. So all of that said, when we talk about wine stability as far as interactions with bottling or packaging, we're not just worried about preventing or avoiding microbiological spoilage. That certainly is a big consideration, but we'd also like the wine that we bottle to retain all of the sensory characteristics that we have spent so much time developing. That's the point of making the wine, to get all these lovely stylistic aromas and flavors that we would like to share with our consumer. Unfortunately, the chemical equilibrium of aroma compounds in wine are very delicate, and the relatively rough treatment that the wine gets at bottling compared, say, to sitting quietly in a tank can make those aroma compounds change very quickly. And so we want to treat it as gently as we can, and then we want to put it in a packaging system that will keep it from changing further for the most part. So, as far as wine aroma goes, once we have got it in the bottle, our biggest enemy is oxygen. And again, unfortunately, there is a potential to pick up a whole lot of oxygen during bottling. We've got a really large liquid surface area during bottling. We have a really high ratio of headspace to liquid in the bottles themselves. There's a lot of splashing going on, and the wine is going through a series of sequential operations like filtering. And at each of those steps, again, we have the opportunity to pick up oxygen. Optimally, we'd like to see less than 0.5 milligrams per liter of oxygen in finished white wines and less than 1 milligram per liter in red wines. But poor bottling line operations can result in oxygen saturation in the wine, which is up at 8 milligrams per liter. That is much higher than we want to see in any wine. And oxygen levels that high will suck up more than 30 milligrams per liter of free SO2. And if your final free SO2 is somewhere around 50 or even as low as 30, that's problematic, because as soon as we drop below 10 milligrams per liter of free SO2, we're at risk of oxidation that's going to lead to spoilage aromas rather than just nice evolution over time in the bottle, sort of the maturation characteristics that we like to see. So, while flushing lines and ensuring that there are no leaks in our bottling operation reduces the amount of dissolved oxygen that the wine picks up, as much as 60% of the total oxygen in the bottle actually comes from the headspace. So we've got about 40% of what's in our wine bottle altogether that's been picked up in the wine, but 60% is in that headspace that we can't avoid. There's always going to be headspace in your bottle. It's just there. This much, or having too much oxygen in your headspace results from inefficient bottle sparging throughout the bottling process. And I hate to tell you, but unless you have a fully automated line with multiple sparging locations, it's very likely that you've got more oxygen than inert gas in your headspace. So this is especially true, of course, if you're doing sort of manual operations and are bottling on a full line, 4-line spout filler by hand, because we just don't have the opportunity there to get all of that gas or to get all of the oxygen out of that headspace. So you probably are looking at quite a bit of oxygen in the headspace rather than in the wine. Although, depending on your bottling operations, there may be a lot in the wine too. So from a research point of view, it's not necessarily helpful depending on what your bottling line operation is, but in an ideal world, we now have a really quick way to take rapid total package oxygen measurements. That's TPO for short. So if you see TPO written anywhere, that's what we're talking about. Cork, which, yes, is the company that makes the synthetic closures, has what they call their NomaSense system. It's this little handheld device that's fairly simple. It involves putting sticky sensor dots at 2 places on the inside of the bottle. There's one mid-bottle and then one up in the headspace. You then take those bottles, run them through your bottling line, just like any other bottle. And at the end, you use a small LED wand, which is that little sort of piece of wire that you see in the hand model's hand in this picture. And you use that little LED wand to read the oxygen pickup at those 2 dots. So this analysis is non-destructive, which is helpful. It used to be that the only way that we could measure dissolved oxygen was actually pulling a bottle, taking it apart, and measuring what was going on in there. So it's much quicker and easier. It gives you a more accurate measurement. And this particular instrument measures from 1 part per billion, that's a tiny amount, up to 45 parts per million or milligrams per liter of oxygen. So it's well within the range of what we want to see, or below which we want to see in our wine. So it's unique and helpful both for researchers and for large winery operations, because you can measure both the dissolved oxygen that's in the wine, as you can see in that lower dot that's midway down the bottle, and also what's going on in the headspace, so you can see where your problems are if you have too much oxygen, whether it's oxygen pickup in the wine itself or whether you just have got quite a bit of oxygen in your headspace. In either case, usually to do a good check on a bottling run, you would pull a bottle at the beginning, at the end, and then about every 30 minutes throughout a bottling run in order to test the oxygen. And that, of course, is not going to be something that's feasible for everyone, especially if you're doing, again, as I mentioned, small hand bottling, but it is something that we would aim for in an ideal world as far as monitoring our oxygen and oxygen pickup during bottling. So using this instrumentation, in 2014, Clark Smith did a really interesting study where he measured both the headspace oxygen, which is shown on this chart in the yellow portion of the bars, and also the dissolved oxygen in the wine, which is the gray portion of these bars, to understand how variable the total packaging oxygen, or TPO, was in wines from different bottling lines. So if you look at this chart, you can see that there are 18 wineries that participated in this survey. They're numbered 1 through 18 along the bottom there, and you can see a bar for each. And then if you look at the y-axis on the left-hand side, you can see that the measurement is then oxygen concentration in milligrams per liter, and it goes from 0 to 4 milligrams per liter of oxygen. So remember, what we're looking for in white wines is less than 0.5 milligrams per liter, and in reds in less than 1. And you can see, if you look across these bars, that really only about 7 of them, look like 3, 7, 11, 12, maybe 15 and 16. So maybe about 6 of them are below 1, and none of them are below that 0.5 as far as their TPO. So we've got oxygen pickup for sure, and that highest one, number 2, is way up there, almost at 3.5. So also the arrow bars, as you can see, are quite big. So not only is there quite a lot of variability from bottling line to bottling line, but also within the bottling line in individual bottles. So long story short, there's a whole lot of variation in oxygen pickup during bottling. It's really hard to guess then how much you're getting. It's kind of like yan. It's one of those things that you can't guess. You're going to have to measure. So if you really want to understand where your oxygen problems are, you're going to have to find some way to measure this over time. So probably not the best news, but reality and something to know. Yeah, that's all I'll say about that, I guess. So I'm going to pull away from data for a minute then so that we can actually do a little review of the types of closures that are available, since that, as I mentioned before, is one of the major bottling decisions that we have to make. Closures are really an ongoing discussion. There are technological advances in both synthetic and screw cap closures that have produced a range of options, many of which offer fine-tuned rates of oxygen ingress. This photograph is an advertising photo from Noma Cork, as you can imagine, and I promise I am not a paid shill for Noma Cork. It's just that they are by far the one of the most widely distributed synthetic corks in the U.S., and so that's one of the things that you're probably going to be most likely to see when you're out looking for synthetic corks. They also do a lot of research, so they have a lot of data out there. But here you can see 2 extrusion molded synthetic corks in the upper left-hand corner. Just to the right of that, there's a 1+1 technical cork, and I'll talk about each of these in details a little bit later. And then in the upper right-hand corner, there's an old-style agglomerated cork. And then again, down on the bottom left-hand corner, there's a microagglomerated, then a colmated, a sort of straight punch, high-end natural, and the injection molded synthetic in the far right hand. All of these will certainly vary in cost and performance, and these are the 2 variables that you really have to balance when you're thinking about purchasing closures. So let's review the various types in some detail so that you understand where they come from and how that can impact the sort of aging that you get when you use them in your wines. So natural corks are, of course, the most familiar. It's really what most people think of when they think about a wine closure. Like, this is the cork that we imagine, not something that is plastic or odd colors. And these are both pictures. This is a picture of 2 high-end natural straight punch corks. You see one on the left that has been is unmodified, and the one on the right has been cut in order to show the interior surface. And then under this cut cork on the right-hand side, you can also see an example of a cork plank. This cork plank is too small, of course, to punch an actual cork out of, but it does give you an idea of the striations that occur, sort of the growth patterns that occur in this bark from the cork tree. I am absolutely positive that everyone is pretty familiar with cork production, so I won't go into great detail. But in short, corks are sections, horizontal sections, cut from the bark of the cork tree. It's a renewable resource that's grown primarily in Portugal and Spain. You can see in this FAO graphic that Portugal produces about 50% of the world's cork, and Spain about another 30%. The rest is generally from around the Mediterranean. There is increasing production in France, I understand. And it's interesting to note that in general, quality isn't based on country of origin. We are not going to be looking at cork terroir anytime soon. Quality is really based on individual trees, so it's highly variable and really depends on the growing conditions from year to year and really from tree to tree. So corks, natural corks are punched, excuse me, I advanced a little bit fast, are punched in the direction perpendicular to the direction of growth. So if you can see on this cork plank, the arrow is pointing from the inside of the tree towards the outer bark edge, and you can see where the corks have been punched at a 90-degree angle and going down in the opposite or the perpendicular direction to that growth. And the reason that we do that is because there are lenticels that are formed naturally in the cork bark. These are open channels that are lined with dead, hardened cells, and they allow airflow to move through the body of the cork. That is clearly not something that we want to happen when we are trying to stopper a bottle. So when we cut the corks this direction instead of the other direction, you get lenticels that run horizontal to the direction or perpendicular, I guess, to the direction of the cork placement in the bottle, rather than from the opening of the bottle down into the part where the wine is. So you can see these lenticels could be detrimental, and there's a sort of a reason behind the madness of how these things are punched. But of course, corks are natural products, and they vary widely, so they're sorted into grades before use. If you're interested in reading all the details about grade sorting for corks, the Cork Quality Council has got a really great webpage, and you can see you can just look up corkqc.com, and you can find all kinds of great information, and it's primarily based on visual guidelines, and in short, you don't want to have a lot of holes or a lot of hard areas where the cork doesn't have its normal flexibility and bounce back ability. So we move from a grade A, which is top quality, all the way down to a grade C and below, and when you get much lower than that, of course, the corks are ground up, or the cork, that piece of bark is ground up and used for other products. So a high-end straight punch cork is going to be grade A, B, or C, and then we go downhill from there. The reason historically that we have used cork is because its structure is really unique in the natural world. It consists of a series of pentagonal or hexagonal cells, as you can see in this microscopic photograph of a cross-section here. They're filled with a gas that's quite similar to air in consistency, and that gas makes up the majority of the volume. So you can tell here that the cell walls themselves are relatively thin, and a majority of the volume of the cork is gas. That makes it very light and very flexible. It can be compressed to half its original thickness without losing any flexibility, and will bounce back to its original shape. If you've ever taken, say, a champagne cork, which is highly compressed, out of a champagne bottle and allow it to sit for long enough, eventually it will pop back out to its regular shape. Cork is also the only solid which, when compressed on one side, does not expand on the opposite side, which is pretty cool. There's some cocktail information for you. Trivia for your next cocktail party. But this property makes it really well suited to holding its shape as a stopper. It can be compressed and pushed into that slender bottleneck, and then we'll push back out in order to seal fairly well with the otherwise, very smooth glass that it's interacting with. Cork is also unique because it's about 45% suberin. Suberin is a complex fatty acid that gives cork cells their flexibility Impermeability and moisture resistance. The impermeability and moisture resistance mean that the cork is really resistant to oxidation reactions and to decay. So unlike wood, which can soak up water and can allow other gases in, cork doesn't do that very easily. So its structural integrity will last much longer than other plant-based substances. To produce natural corks then, high-quality natural corks, like the ones you see in this picture, which are rather long, cork planks are boiled to remove any organic objects or other matter, and also to expand the cell structure that makes them more appropriate for this use. They're then stacked, allowed to dry in a sterile area for a few days or so, cut into strips, and then punched, as you saw earlier, either manually or by machine. Because we have this history of cork taint and other concerns, a sample of each cork batch is quality tested, so a statistically significant section of each batch of corks is tested. And then the stoppers are polished, so they have their very smooth outer surface. They're usually washed in hydrogen peroxide and then slowly oven dried, and then covered with a film of either paraffin or silicone to ease both insertion and extraction. Then they're packed in bags filled with sulfur dioxide and sealed up for shipping. So they do have a little bit of SO2 in there to prevent any contamination, as you've noticed if you've ever opened a bag of sealed corks and gotten, the inside of your nose blown out by that whiff of SO2. So if this is our simplest, most natural cork product, I would say that the first level of sort of manipulation are colmated corks. Colmated corks are lower grade single piece corks, so maybe a grade 2 or grade 3, that have been treated to seal lenticels and other blemishes. So if you look at these colmated corks in the picture, you can see that there are significantly more pits and lenticels that have been covered over and are now sort of the same color as the cork, rather than being the darker color of the bark cells that normally line those lenticels. That's because the corks, once washed, are then placed into a tumbler with an adhesive and some finely ground cork dust. They're tumbled around for a bit, and then this coating covers everything in the cork. It seals up any flaws or holes in lenticels and covers the blemishes. So you get a very sort of uniform color because it's all that lighter color of the cork dust. They then are, of course, polished and sanded and everything else that needs to happen to finish them. But it gives you still a natural cork product that is less expensive than a premium quality cork, but still performs about the same way. So moving on to sort of more processed cork products, we find the agglomerated corks. Agglomerated corks are made of cork particles that are held together with food-grade adhesives. After the washing process, the cork used for these is pulverized and then screened to separate fragments that are between 3 and 7 millimeters in diameter. So yes, it is lower grade corks and also sort of bits of cork scraps that are left over when we punch out the higher grade corks. The agglomerated corks are generally then extruded. Extrusion is how we make several food items like cheesy poofs, Cheetos. So they're extruded into this shape and chamfered, as you can see these particular ones are, and then finished in processes like those used for punch corks. So they are washed and polished and coated so that they're easy to insert and extract. Arguably, these corks are the least durable of the current options. They do seem to have a tendency to crumble more easily than pretty much any other cork product, likely because they're these fairly large pieces of cork that have been stuck together. So these are the ones that if they're used in bottles that are aged too long, may disintegrate when you put a corkscrew into them. So they are much cheaper, but also perhaps not the highest quality. Interestingly enough, and I mentioned this just in case any of your consumers come to you with this concern, in 2015, there was a brief scare when some articles, actually ended up being probably one article that was pushed around a lot, was published that suggested that the adhesives that are used in agglomerated corks were potentially dangerous. The claim was that since they were exposed to wine over time, the alcohol in the wine would extract some of these adhesives into the wine, and that was toxic, and so on and so forth. But this was pretty quickly cleared up. It turned out to be false news. I hate to use that term the way it's used these days, but it was sort of a non-story, and there was some suggestion that an unnamed synthetic closure company that was sort of trying to get a little bit more market share was spreading some exaggerated claims in order to hurt their competitors. So if anybody comes to you with that concern, you can say that nope, absolutely, everything is food grade and everything has been approved and there is no danger in this area. So always good to have a little bit of mythbusters when it comes to unwarranted wine scares. So technical corks are sort of an adapted agglomerated cork. They are majority agglomerated cork, and then we'll have discs of natural cork on the end. So you can see in this particular example, there are 2 discs down here on the end. These corks pictured are actually sparkling wine corks. Sparkling wine corks are almost always technical corks because it's helpful to have sort of that agglomerated, easily compressible top part, and then a little bit more boundary or security down there at the end where the end of the cork is touching the wine. In most cases, well, in several cases, there will be 2. As you can see here, you can kind of tell, you can see the seam. There are 2 different individual discs at the bottom of the agglomerated portion of the cork. If there are 2 discs used, they're usually rotated 90 degrees so that if there are any lenticels, those lenticels won't move all the way up through to the agglomerated portion. It just gives you sort of a better, more security as far as oxygen ingress into the cork. The idea, of course, of these agglomerated or these technical corks is to offer a closure that's more affordable, but which puts a piece of solid cork in contact with the wine. You may find technical corks with discs on both the top and bottom. Those are often called 1+1s, or just on the end inserted into the bottle. So I'm sure you're familiar with these. I showed you one also in that very first picture showing all of the corks. That was a 1+1. Along the lines of agglomerated corks, there's now a lot of use of micro-agglomerated corks, particularly of the Dept brand. These are interesting products. In addition to being micro-agglomerated, which means there are much smaller cork granules used, they're little granules from 0.5 to 2 millimeters in diameter instead of the larger 5 to 7 millimeters. They're molded together still with food-grade adhesive, but in the Dept production, they also include synthetic microspheres, which help to hold the whole, like sort of glue everything together and give you both a cheaper product, less chance of TCA, they claim, and also just a sort of a mixed natural plus synthetic product. These are relatively popular and seem to be performing quite well. They also are marketed in a range of densities, which they say are designed to allow a predictable amount of gas exchange as the wine ages. So if you want a little bit of oxygen ingress, but not too much, they offer you a range of options. Marketing suggests that these Depts are good for up to 60 months for bottle aging. I have not seen an independent study that actually tests that number, but those are their claims. And also, it's interesting to note that the Depts don't just, when they clean and pulverize the cork, they actually remove all of the lignin, which is the woody portion of the cork that also is, you know, in other wood products like barrels, and just leave the suberin, that very spongy, flexible and waterproof portion, and that's what is mixed back up into the cork. So it's really almost a pure suberin plus synthetic mixture, which is pretty much interesting. So that's it for products that include cork. We'll move now on to non-cork products. There are 2 types of synthetic corks that are commonly on the market. The first synthetic corks available were injection molded, like the ones that you see here. And injection molded corks can be identified because they either look a little bit like microagglomerated corks, or they look kind of marbled on the outside. You can see the seams and swirls where the plastic or the polymer fills into the mold. So they look marbleized or opalescent depending on the color. The injection molded corks are growing less and less popular, mostly because if you've ever tried to pull them out, you know they're ridiculously difficult to pull out of the bottle. These are the ones that consumers complained about because they would not come out. And also because they're consistently found to allow excessive air to enter the bottle over time. Like, these are the closures that just allow air in a rushing wind almost, it seems like. So these are problematic compared to most other available synthetics, or most other actually closures. In contrast, the extruded synthetics, like the one you see here, are made of a spongy inner core. It's like a honeycombed inner core. You can kind of see in this picture that there's a difference in the end of the cork than there is on along the outer edge, and then a flexible outer skin. So you've got two different consistencies of polymers there, and the outer skin is designed to act more like a natural cork in that it expands and interacts with the walls of the bottleneck. If you are interested in how this is made, or just sort of like watching those kind of videos, No More Cork does have a pretty cool video, a short video that shows you the process. So if that is down your alley, it's definitely worth a little watch. Most synthetics are made of low-density polyethylene, which is LDPE. LDPE is resin code 4 for recycling purposes. So in theory, all of these synthetic corks are recyclable. In practice, however, most municipalities don't accept LDPE for recycling, although the number that do is slowly growing. So if you make the choice to move to synthetic corks for, green reasons, I guess, if you decide they're for some reason greener than corks, make sure that you actually can recycle them where you and your consumers live, or that's not going to work very well. Also, just a quick note, much like natural corks, synthetics are also coated in either a silicone or paraffin coating. The exact makeup of this coating is confidential, but they do also put a coating, a sealant on the outside so that they're easier to insert and extract. So finally, for the closures I'll talk about today, they're screw caps. And screw caps, of course, 15 years ago or 20 years ago had a horrible reputation, but they have just improved in leaps and bounds. Screw caps in general are made of aluminum. They will have an inner lining up there in the top of the cap that is made of some sort of polymer. Usually they are originally designed to be neutral and completely block any gas exchange with the wine, but today there are all kinds of engineered liners that contain some oxygen and allow some oxygen to move slowly into the bottle and ostensibly allow predictable amounts of oxygen to interact with the wine. Again, we don't have a ton of long-term studies for that, just because they haven't been around long enough and there hasn't been enough independent work done. But you should be able to find screw caps today to suit a variety of needs, and they certainly are much better than those available even 10 years ago. They're going to continue to improve. So keep your eye both on improvements or new technologies in screw caps and in synthetic corks, because you're going to see all kinds of different things offered pretty soon. Screw caps now are about 15% of the market worldwide, and they are growing, so we'll see much more of them. I am not today going to talk in detail about Venlock, which are the glass teacaps, or the Zork, which is relatively popular. It's a 3-part system that's popular in Australia, simply because they're pretty expensive and pretty rare. If those are things that are really interesting to you, you can always drop me an email and we can talk about those. But for the most part, these are the packaging closure options that I'm going to talk about. So since we're at like a 40-minute mark, if anybody has any questions right now, I could take them. Otherwise, we can go on and talk about some of the post-bottling oxygen issues that we run into with these various closures.
Thanks, Anna Catherine. Yeah, if you have any questions, feel free to use the chat bar in the lower right side of your screen, and make sure you send your questions to everyone so that everyone can read your questions.
Nope.
No questions? Yeah, feel free to move
All right.
on, Anna Catherine.
Okay, we'll move on because we are kind of tight on time. So if you think of any, type it down, and Alex will shoot it at me at the end. So let's move on and talk about post-bottling oxygen, because as I mentioned, oxygen is probably our biggest threat when it comes to preserving the sensory characteristics that we want in our wine. So let's talk about the phases of oxygen ingress into bottles. It occurs in 2 phases post-bottling. For natural and synthetic corks, the first 1 or 2 months show the most rapid increase in oxygen in the bottle, and we're pretty much pinned down the fact that it's the sum of air that's forced into the bottle during the closure, so when we're actually inserting whatever the closure is into the bottle, or trapping it under a screw cap, of course, and whatever is expelled from the closure itself, because in both synthetic and in natural corks, of course, there's a lot of empty space. Otherwise, we couldn't compress it. So when we do compress it, we push a lot of that oxygen or the gases out of it, and that continues to be forced out as the closure remains compressed for a couple of months. Then in the second phase, in phase 2, we start to see oxygen permeation through the sides and or the body of the closure, depending on what that closure is. So ingress during phase 2 is almost entirely dependent on the types of closures used, and we'll talk in detail about how each closure interacts with or what kind of risks you have with each type of closure. For screw caps, we pretty much only have a phase 1 because screw caps still are sealing the bottle entirely, although as I mentioned, there are sometimes liners that have some oxygen in them. So anything that's happening in phase 2, if there is phase 2, is actually an interaction between the lining in the closure and as that moves into the bottle and into the headspace. So let's talk about phase 2. What do we see? In 2001, there was a seminal study at AWRI, which is the Australian Wine Research Institute, where they looked at the performance of all kinds of cork types and monitored the loss of SO2 over time. So since SO2 loss is proportional to the amount of oxygen in the bottle, what we are looking at in these charts is the lower the concentration of SO2, the more oxygen is moving into this bottle or is present in the bottle than is being, interacting with the SO2 and pulling it out. So you'll see here, there's actually a left and right side to this chart. Along the bottom, you'll see the storage time in months from 0 to 18 months, so we're out to a year and a half. And then on the y-axis, you'll see its concentration of free SO2 in milligrams per liter, and that goes from 0 to 32 milligrams per liter. So at bottling, the wines that were put into these bottles and then closed were between 30 and 32 parts per million or milligrams per liter of free SO2. So as I mentioned before, we have a problem in our bottle aging when SO2 concentration drops below 10 milligrams per liter. So I've put a dotted line right here at 10 milligrams per liter, so you can start to see which of these corks are problematic. And you can see that at 18 months, SO2 in the natural cork references, which are listed there as reference 2 and reference 3, and they're the closed and open triangles, that was still above 10 milligrams per liter after a year and a half, as was the 1+1 technical cork over on the right-hand side, the open triangles. So a technical cork 1+1 would be agglomerated in the middle with a disc on either end. And then also the agglomerated cork, which is the red circle, the closed triangle that's right above those 2 natural references. So the agglomerated cork actually performed a little bit better than did the 2 reference natural corks. There was 1 screw cap as well that was tested. I've circled it there in blue, and it performed very well. It, of course, had the highest amount of oxygen, or lowest amount of oxygen after 18 months, as we expected. And it's important to note that with all of the natural corks and screw cap and some of the synthetics, there was a marked decrease in SO2 for about a year, and then that leveled off. But for the synthetics, it continued to drop. So this is pretty typical. What we see after about 12 months is that we see a real slowdown in oxygen ingress into corks that are not flawed, and of course the screw cap, whereas the synthetics continue to go down. So all of the other corks, all of the other lines that you see here are a variety of both extruded and molded synthetic corks. A lot of them, these are all the products that were available in Australia at the time, so it's now been almost 20 years. A lot of these are now even not made anymore because they were not great products. But please realize that the technology used to make synthetic corks has certainly changed since these were produced, but we did at the beginning see quite a bit of difference. So ever since this study, we've been paying a lot of attention to synthetic corks and the amount of oxygen that moves into the bottle when they're used, and producers of these corks certainly are aware of that, so they are working continuously to make these products better and more useful. We've also known for years that natural corks will express oxygen into the bottle for a month or two after bottling, as I mentioned earlier. That's phase 1. But until recently, we weren't really sure that that happened with synthetic corks as well. So this 2013 study came along. They compared oxygen ingress in synthetic corks and with a screw cap. So you can see CoX1 and CoX2 are both extruded synthetic corks, and then the SC is a screw cap. And you can see that the oxygen, oops, it's not going forward. There we go. The oxygen increased most rapidly in the first 2 months. So along the bottom there, we see months after bottling. And our measurement now on the y-axis is not SO2 milligrams, but it's oxygen milligrams. So now we're looking at an inverse scale. So the more oxygen, the worse things are, at least for our purposes. So after the first 2 months, we see a pretty rapid increase, and then it slows a bit, suggesting that all the oxygen that was in the corks, most of it had been pushed out, but yet we are continuing to see oxygen moving into the bottle, even after everything that was expressed in the cork is out of it. So that still means that we've got something moving into the bottle here. It's a little bit interesting that the screw cap still is increasing, but if you see the numbers are very low, I mean that screw cap is still like less than 1, so that's a pretty low number. You can also see that over time, the two synthetic corks allowed very different amounts of oxygen to move into the bottle. Synthetic cork 2 is about twice as high as synthetic cork 1. And if we consider that it takes about 4 milligrams of SO2 to consume 1 milligram of oxygen, that means that synthetic cork 2 is consuming about 15 milligrams of free SO2 compared to around 6 milligrams of cork 1 and 4 for the screw cap. And of course, the nature of all of these studies is that they won't tell us what these products are for fear of getting in trouble, but you can see that we do have variability among synthetic corks, which sometimes can work to our favor. A really interesting bit of data that's come out in the past few years as well was a study in 2013 that looked at oxygen ingress in natural cork. We felt pretty confident that all of the studies where we compared natural cork to synthetic corks showed that oxygen ingress over time is lower in natural than in synthetic. But in almost all of those studies where we compared screw caps or synthetics to natural corks, only a few examples of natural corks were used. The researchers were kind of assuming that natural corks are relatively homogeneous. So one natural cork is going to act about like another natural cork, like the screw caps and synthetic corks were. However, this was not a good assumption to make. This 2013 study looked at more than 600 natural corks, so that's a really great sample size. And the range of oxygen ingress over the course of a year was found to vary from 0.5 milligrams to as high as 3.5 milligrams. So looking at this chart, you can see that now we're measuring time in days. So it goes from 0 to 360 over on the right. And then on the left-hand side, we're looking at oxygen in milligrams from 0 up to 4. So again, that's half. 8 again is what is saturated, and we really want it to be below 0.5 for whites and below 1 for reds. So this difference is a there's a difference in free SO2 consumption of about 2 to about 14 milligrams, and that actually is similar to what's found in studies in synthetic cork. So it's kind of a surprise to find that the variation in a high-quality natural cork can be almost as high as we see in some synthetics. However, an even bigger study that was performed in 2015, you can see here, that was published in Practical Vineyard and Winery, so that should be available if you can find it online. It suggests that oxygen transfer over time is still lower in natural and technical corks than it is in synthetics. So even though we've seen quite a bit of improvement in synthetic cork performance, we're still seeing better performance in both agglomerated, technical, and natural corks. In this study, oxygen ingress was studied over 2 years. The bottles were stored horizontally at ambient temperature. So you can see that the oxygen transfer rates were lower in the technical corks and in one of the screw caps you see on the left-hand side of this chart, and were much higher in the synthetic corks that are over here to the right. And you notice that they were very specific in what they measured. They chose several of the diam range from 2 to diam 10, and also several of the NomoCork range. So they're going from Select 100 up to NomoCork Light. This chart is a little bit more frustrating to read in some ways, because you can see on the left-hand side that they actually are measuring oxygen transmission rates in milliliter per closure per day. So instead of giving you the total oxygen ingress or SO2 loss over time, they've averaged it, and you can see about what's happening per day. However, if you go and look at the spec sheets for any of these products, the diams and the NomoCorks in particular, as well as I didn't look up, I have to admit, I didn't look up the screw caps before the other two. They actually will report their calculated or their tested transmission rates, their OTRs, in these same units. So for instance, the diam 2, which is all the way over here to the left, reports that they have a maximum of 0.5 to 0.35 milliliters per day, and you can see that in this study over 2 years, it actually was much lower than that. The same holds true with diam 10, which the company reports is about 0.07 milliliters per day, and it's way lower than that. So diam, it sounds like, is hedging their bets, and they're actually reporting perhaps a little bit higher oxygen ingress than at least was found in this particular study. NomoCork seemed to be right on the money with their spec sheets. Just for example, I pulled up the NomoCork Smart, which is the second to the right yellow column over there, and they report 0.0076 milliliters per closure per day, and you can see that's pretty much right on the money. It's showing up right there between 0.06 and 0.006 and 0.008, so that's about right. So they seem to be reporting at least what was found in this study. So the good news there is absolutely sounds like we can trust what these companies are reporting, and they are in good faith, trying to produce and report corks that have a range of activity. And you can see that there was certainly slightly increasing or decreasing ingress as we get higher up the range in the diams, and decreasing ingress as we move from the NomoCork Light down to the NomoCork Select 100. So quite a bit available there. So kind of the question at this point is, all right, we know we have oxygen and that it's moving in different ways, but what does that mean for wine aroma? There have not been a ton of studies on this, but there have been a couple really good ones. In a 2005 study, Sauvignon Blanc wines were aged for 2 years under screw cap with 2 levels of free SO2 at bottling, 20 and 30 milligrams per liter. So if you look up there in the key, you can see that the black bars are screw caps with 20 milligrams per liter. The gray bars are screw caps with 30 milligrams per liter, and the white bars are corks with 30 milligrams per liter. And chemical analysis over time, after 2 years of aging, showed that some of the thiol compounds that are typical and desired in Sauvignon Blanc. The sulfur compounds that produce passion fruit, for instance, did decrease over time in the wine closed with cork, but when they took this information and ran it through a sensory panel, consumers couldn't really tell the difference. So we have different levels of SO2 and different closures, and we were not getting significant differences in sensory as far as consumers were concerned. It is interesting to note that this and other studies suggest that natural corks, at least, can actually sorb some sulfur-containing compounds, and we certainly have studies in vitro that show that's the case, but whether they sorb enough of these thiol compounds to make a difference either in removing good or bad aromas, it doesn't seem to be possible. They just don't sorb up enough that it will make much of a difference. So while there is some interaction there, probably doesn't make a difference to the consumer. There are also a few studies that show that synthetic corks have the ability to scalp aromas, to pull aromas out of the wine. But again, we don't have enough robust studies to show that those sensory changes are perceivable, at least not to the average consumer, perhaps to a highly trained winemaker who knows his wines very well. But at this point, that seems to be a minimal risk compared to other things that we might worry about. In a similar study, also on Sauvignon Blanc, that was performed over 2 years, it became clear that the oxidation character down here on the left was highest in the synthetic cork. And if we look at this chart, this is a radar plot where each of these colored lines represents the intensity of various attributes for wines aged with different stoppers. So the yellow line is going to be the synthetic cork. And you can see that yellow line is poking way out with oxidation, indicating that the synthetic cork let in way much more air than any of the others. Overall fruitiness, freshness, and aromatic intensity were highest in the cork and screw cap closures. So you can see the orange, that's the Saranac, the green colmated cork, and so on, are showing like higher scores over in the fruity freshness or aromatic intensity. And it's also notable that the tin-lined screw cap, which is in the red line there, had retained quite a bit of aromatic intensity, but also showed the highest level of reduced aromas. So, you know, over time, sort of oxidative character and reduced character are two different ends of aroma development. If you don't have enough oxygen, you tend to move towards reductive character. These are characters that are produced, of course, during fermentation, but sort of lie dormant as precursors are similar unless they're aged in a highly reductive environment. So they can raise their ugly heads at potentially too high levels if there isn't enough micro-oxygenation happening. Do note that the black line that's showing the highest reduction level was actually the test, the control, which they're labeling as a bottle ampule. And this is sort of the non-practical, take your wine, seal it in a glass bottle where there's nothing, you know, all air is extracted, and then we melt the glass over so you've got a hermetically sealed ampule. So it's for sure is going to show us the highest reduction notes and the lowest oxidation because it was all glass, so there was no oxygen getting in there. So this study, as well as the summarized wisdom of several studies over the past few years, suggests that closures with high oxygen transfer rates, or OTRs, like synthetic corks, are most likely to result in oxidized characteristics over time, while really low OTR closures like tin-lined screw caps can promote the development of reduced aromas. Things in the middle, however, like low OTR closures, like all of the cork products, lead to a retention of fresh and fruity characteristics. Those don't go towards oxidation, but without the development of reduced aromas. So using something somewhere in the middle there, like the natural products where you get a little bit of ingress, seems to be the best for most wines. However, it depends on how long you're going to age the wine. I just want to touch on before we're done that menace of natural corks, which is TCA or cork taint. As a review, cork taint arises when phenolic compounds, like the phenol here that occurs naturally in cork as well as wood and paper, interacts with bleach, forming a chlorophenol. The chlorophenol then is acted on by specific microorganisms if they're present, usually molds and penicillium compounds. And these microorganisms are capable of converting that chlorophenol into a chloroanisole. And chloroanisole, like trichloroanisole, are a family of stinky compounds that we generally call cork taint. There's an interesting effect that we have learned recently, is that the movement of TCA through closures is quite different. This is a different problem than that of having a TCA-affected cork. If you use a cork that is infected with TCA and you put that into a wine, you absolutely are going to have movement of the TCA from the affected cork into the wine. But recent work has shown that if we have TCA present in a winery from other sources, which includes tainted wood, tainted cardboard, or even bacterial problems in drains, if the TCA concentration in the air is high enough, it can actually move through synthetic corks and some screw caps to enter the wine itself. There are just a few studies on this, but with synthetic corks especially, we get this movement, which is not what we want. Coincidentally, or ironically, depending on how you want to look at it, when environmental TCA reacts with natural cork, it seems to be sorbed into the outer layers of the cork and doesn't move through it into the wine. So synthetic corks aren't a perfect defense against cork taint because of the TCAs in the environment and not in the cork itself. It can actually move through the synthetic cork, but then is blocked by the cork, the natural cork, which we used to think was the sole and only cause of cork-tainted wine. So that gives you something fun to chew on when you're worried about TCA. So just to summarize, when we're preparing for bottling, the best management practices include proper SO2 management, appropriate pre-bottle cleaning and sanitation, and a good understanding of oxygen exclusion during the bottling process. Again, this is something we could talk about for several hours, but certainly are things that you need to remember. And then from the closure selection, you need to think about the type of wine that you're bottling. Is it something that is going to be drunk relatively rapidly? Aging period is important. If it's a white wine that's meant to be drunk within 6 months to a year, you can go synthetic or screw cap, no problem at all. If it's a red that needs to be aged for much longer, you need to think more carefully about what you want to use, because you probably do want a little bit of oxygen moving in, but not so much that the wine goes to an oxidative state too early. And of course, the cost. I mean, we know that some of these things are very expensive. The cost of a natural high-quality cork compared to a colmated or even a synthetic is quite different. So you need to calculate what you're going to get per bottle, what the wine is worth, and then how much protection you need to keep that wine for the amount of time that you want it to be kept. So that said, I hope that brings you up to date on the research that impacts wine aging. And I do want to thank some of my Enology colleagues at Cornell. Dwayne Bershaw is a lecturer, Gavin Sachs is our wine chemist, and Chris Garling, my extension colleague. We talk about these things quite a bit, so I didn't want to take the credit for all of this work because all of them have chipped in at various points, and I can certainly take any questions?
Great. Thank you, Katharine. So we have a couple minutes for questions. Continue to submit them using the chat bar. Just make sure that you set your chat bar to everyone so that everyone can see your questions. So let's see. We have a question from Douglas. Do you have any recommendations if you're bottling an organic wine?
I'm guessing that you mean recommendations for closures. But to be honest with you, an organic wine doesn't need to be treated differently than any other wine. To my knowledge, there are no rules as to whether you can use synthetic or natural. I don't think organic regulations extend to packaging. So just like any other wine, you want to think about how long it's going to be aged. If you have an organic wine with low SO2, I would be more concerned about oxygen getting in there. So you not only need to think very carefully about your bottling line practices, but also you probably want to go, towards probably a screw cap or something that is really going to give you synthetics, I'm afraid, might have the potential to give you too much oxygen ingress because organic wines generally have low SO2. So I hope that answers your question. If you need more specific information, go ahead and, type something more in, and I'll do the best I can. So Todd says, ageable reds under screw cap. I think that the jury is still out on that. There are some long-term studies that are going on, and as I mentioned, screw caps are improving so rapidly that by the time we finish, say, a 10-year aging study, the technology is all different. So I think most people now, to be safe, are still not using screw cap because we have the risk not only of going towards those reduced characters because we don't get the oxygen that we want to interact with the tannins and some of the other ageable compounds in reds, but also, and this is just me thinking as somebody who has packaging classes, not someone who is a specialist in screw caps, but especially if those red wines are stored horizontally, there's a lot of alcohol in wine. And so if that's interacting over time with polymers and aluminum, I think you have the potential for some degradation to happen and potentially then tainting. But again, like I said, that's just off the cuff. So I think folks are still working on that. I know there's some studies in Bordeaux to see how that goes. I haven't seen robust, reproducible results on that yet. So I apologize for not having a pat answer for you, Todd.
Great, thanks for your question, Todd. We have a couple more minutes for questions. Bill sent a question to me, and you sort of touched on this already, but with natural cork, what trends are you seeing in the frequency of cork taint?
It seems to be going down overall just because we finally understand what levels of QC need to happen. The number, even when I tried to go and look up the most recent numbers for incidence, and it ranges, I've seen everything from 2 to 5% to like 3 to 7%. So it's relatively low, but I think it's really hard to get good numbers on that. So, a reputable dealer, stay away from chlorine. Most good quality cork suppliers understand the steps that they need to go through in order to avoid TCA. So I honestly think that we're seeing more of an incidence of TCA occurring in wineries from places other than the cork, like people not understanding that they need to not use chlorine even in their drains because there are some bacteria that can live in drains that can produce TCA and then that gets in the environment. So it's relatively low. It's certainly still a risk, and it's certainly still expensive. So the diams are often a product that I find people using if they are worried about TCA incidents because those diams are so well processed and cleaned, but act like a natural cork in many ways. You saw on that study, the 2015 Lopez study, that they are acting in a bottle as far as oxygen ingress, much like a natural cork. So if TCA is a concern, that might be something to consider.
All right, well, if anyone does have additional questions, feel free to email me or Katharine. I'll include our emails on the chat bar. Todd says, thank you, enjoyed it. And Alistair says, an extremely interesting presentation, thank you, not using synthetic corks for the long term. All right, so thank you again, Katharine. I really appreciate your time for both the webinars today. I'd also like to thank all our participants and sponsors who have made the this year's Northern Grapes Project webinar series possible. As a quick reminder before we go, the webinar series will continue on Tuesdays of each month through May, which is next month. Be sure to visit our Facebook page and feel free to email me any additional questions that you may have from today's webinar. The next and final Northern Grapes webinar, introducing Itasca, Minnesota's new cold hardy white wine grape, is scheduled for Tuesday, May 9th with Matt Clark and Jennifer and John Tull. According to the presenters, Itasca is lower in acid, exhibits improved cold hardiness, and should be suitable for making a dry style white wine. This seminar will discuss the characteristics of this new variety, including tasting notes, growth habit, and juice chemistries. Slides and a recording of this webinar from today will be posted on the Northern Grapes Project website, as well as our Facebook page in the next few days. Thank you again, Katharine, and thank you again for all the participants, and have a great night.
Thanks, everybody. Good night.